Good morning. Welcome to Krishna's classroom. In this talk, we explore the proof of the Lusin's theorem and, if possible, one of the corollaries. Now, last time we had an overview of this result and then explore what exactly it conveys. In fact, it says if f is a complex valued measurable function on x, and if A is a measurable subset of x such that mu A is finite, and f is 0 outside A, and with epsilon positive, the measure of the set, there exists a continuous function g with compact support on x such that the measure of the set of all x for which fx is not equal to gx is less than epsilon. It says the measurable function is a nearly continuous function under some conditions. This is what it says. Okay, that means you can approximate it, not really approximate, you can approximate it in the measure, this particular function f, by a continuous function with compact support such that the set of all x for which fx is not equal to gx can be made as small as you please. So the choice of the g would depend on how close or how small you want this particular set. That means much sharper approximation in measure would be enabled by choosing is possible by choosing the appropriate g, or there exists such a g. Now, the second part of the theorem, it says that we may arrange this in such a way that the supremum of g is less than or equal to supremum of f on x. So, this is the content of the theorem. Essentially, how near the measurable function is to a continuous function is described here. Okay, so that's the statement of it. Of course, what you have is x is given, then you see that using Rees representation theorem, we discover a class of Lebesgue measurable sets, what is called Lebesgue measurable sets, with the Lebesgue measure. So this is the measure space. Script m and mu are coming from what is called the Rees representation theorem. It's a consequence of it. So that is the place where everything is placed. Now f is a complex valued measurable function. And of course, A is a subset or an element of M with mu of A is finite. That's a crucial. And we assume f is 0 on A component. and for any x, any epsilon positive, there exists G belonging to CC x such that mu of that means the set on which this f and the continuous function differ can be made as small as you please by the choice of the continuous function. So for any epsilon, there is a corresponding choice of G. Now this is what we are going. So it explores essentially how close the measurable function is to a continuous function. So let us prove this. Proof runs through some 2-3 stages. First we assume f is non-negative and bounded by 1. So for this function we prove the result, and A is compact. Okay. Now before that I want to make a remark. The remark is that RK is a example of a standard choice for X, which gives rise to the standard Lebesgue measure on that, and this becomes the usual Lebesgue measure on RK. Okay, right. Now that's of course a complete measure. And see, the speciality of RK is that, which we are not assuming in general, is that we assume we have RK sigma compact, and that property is not necessarily true for a choice of X, and accordingly there are some changes as we have already explored earlier. Okay, so we start with a function which is real valued now between 0 and 1, and A is compact. Okay, it's a non-negative function. A is compact. Then of course we have, what we can do is we approximate f a sequence simple functions such that f is bounded above by f, and all these are simple functions and not necessarily not continuous. Okay. And a sentence to infinity. Now, is this possible? First of all, I mean, we have already seen it earlier and explored it. Okay, the way in which we do is I'll just very briefly explain how this is done. Okay, so let me just remove this. Statement is already clear. What one do is we construct a sequence of simple functions as follows. This we have already done. Okay, how do we do this? Let us take the real case, say one-dimensional case, then it is clear how these things are coming. Now we are talking about a function. We'll take the interval to be a b. Okay. Now I am just taking a special case. Now what we do is we look at the graph of it. Okay. And f is just a measurable function, not necessarily continuous like the one I have drawn, but just to explain to you how exactly we work on this. So we are taking 0 to 1. That's a range. What we do first is take the range and subdivide this to 0 to half and half to 1. This is first. Then what one does is, see, try a line. Now you see that wherever the function is below this, below half, this is the place where it is less than below half or less than half. Now you see that here you take the function, define the function to be 0, and over here, and then these what I have marked with this orange color is that the function is 0. Okay. Now what I do next is, and on the complement of that, the function lies between half and 1. There I take the function to be equal to half. Therefore, the S1 takes two values, namely 0 and half. And there is some subset on which it takes the value 0, and on some other subset it takes the value 1. So this is where it takes the value half. Okay. Now what is the next stage? The next stage is this. You divide this further to 1, 0, 1/4, 1/2, 3/4, and this is the partition. Okay, and then once again you do the same process. Okay, wherever the function takes the value less than 1/4, you set the function to be equal to S2 to be equal to 0. Okay, as you can see, This is quite easy to work out. Now, this is a very standard process. So here you take the function to be 0 and then S2 between 1/4 and half, the set on which the function takes the value between 1/4 and 1/2. The function S2 is taken as 1/4. And between half and 3/4, the set on which the function takes the value half and 3/4, set the function S2 to be equal to half. And where the function takes the value 3/4 and 1, you set the function to be equal to what? Equal to 3/4. Because we are taking a bounded function right now, bounded by 1. Therefore, this is the scenario then. Okay. After that, what you do? So you have S1. This is associated with 1/2. S2 is associated with 1/2 square. And S3 is associated with, and so on. That is the interval. That is the range. And then work out the step functions. Okay. Or what you call simple functions, which possess the property that 0 is less than or equal to, S1 is less than or equal to, S2 is less than or equal to, etc. And it's all below. Okay. So we get this. This is how the simple functions are constructed. Okay. And this sequence of functions do converge to f as n tends to infinity. This is okay. Now we put T1 equal to S1, T2 equal to S1, and so on. Tn equal to Sn minus 1. For n equal to then you can easily see that the following: 2 to the power n, then for n equal to 2, 3, etc., Tn are such that that 2 to the power n Tn is the characteristic function of certain set Tn. Okay. Tn contain. How does that come? For instance, you take S2 minus S1. If you take S2 minus S1, see, this is your S2. So you see, if you take this one, see, on this set, the function is going to be you can find a set on which the function is going to be. So how does this come? See, you have the function monotonically increasing, and you see that there is the set on which the function takes the value, Tn takes the value 1 by 2 to the power n, and the rest of the place it is going to be 0. This is what happens. Okay. So when you come to, that is why this is removed. S2 from S2, S1 is removed. Then look at T2. Actually work it out, then it will be clear. Okay. So there is a T2 on which, capital T2, on which T2 equal to 1, and on the complement of T2 complement, T2 equal to 6. So for that you can compute. So you have got associated with a set capital Tn, which is a subset of A, measurable subset. So there is no problem. Now on that, the function takes the value 2 to the power no, T2 is not equal to 1, T2 is 1 by 2. Square. Okay. Therefore, what you get eventually, T square or 1 by 2 square equal to 1 on T2 elsewhere. So in general, what you have is 1 by 2 to the power n, sorry, 1 by 2, 2 to the power, okay, 1 by or 2 to the power n into Tn is identically equal to 1 on Tn and 0 in Tn. So this is a characteristic function of the function. Okay. Therefore, this is one observation that, okay. Now let us try to work this out, and you see that Fx equal to Tnx. Because what happens is, you see, you have Sn converging to F. So you have, so what you are doing is to start with T1. T1 is S1 minus S0. S0 is 0 plus S2 minus S1 plus this is equal to S1 plus and so on. So what happens is you see that this cancels, and so on. So this is essentially limit of and that's equal to fx because of our property. So we have observed these facts. Now we shall try to construct G. Fix an open set V such that A is contained in such a set exists. Okay. And we put it two things here. One such that V closure is compact. V closure is compact. And so you can get a superset, an open superset for A with the property that V closure is compact. Okay, V open and V closure compact. Now this is all possible because of the structure of the space. Because you know that we are assuming X is housed off locally compact these properties are there. So the topology on X has this particular property. So this comes from this. So you can have an open set which is a superset of A, and the open set can be so chosen such that its closure is compact. Now that is for the whole of A. So the scenario is this. This is your X, not necessarily bounded. Don't get carried away by the Venn diagram. Okay, and then A is a bounded set. A is such that now what we are doing is we are finding out a V open such that V closure, this whole thing is compact. V closure is compact. Now you take Tn. What is the property of Tn? Okay, let us take Tn. Okay. Now we take Tn, right? Now there exists a compact Kn such that now what you have is Kn, which is compact, is contained in Tn, is contained in so Tn is squeezed between a compact set and an open set. Okay, we can also choose Kn and V such that the measure of so epsilon is the given epsilon in the theorem. Okay. So you can choose V and Kn such that the measure of V minus Kn is less than 2 to the power minus n epsilon. Okay. Now we can apply Unison's lemma. There exists functions Hn such that Kn is subordinate to Hn and that is subordinate. Okay, let me do this. Right, in between, so what we do is we can n Vn which is contained in. So this is actually this. So Vn and see this is going to be, so you have Tn now. This is Tn and inside you have the K. This is your K. And you have a Vn which is open and choose Vn so that this particular region, the measure of this particular region is less than 2 to the power minus n epsilon. Such a choice can be made. Now apply Unison's lemma and there exists functions Hn such that Kn is subordinate to Hn and is subordinate to Vn. Now what is the meaning of this? The meaning of this is this. See, Hn Hn has compact support, is continuous and having compact support in Vn. Okay. What more? You have this part tells that Hn is identically equal to 1 on K. Okay. That is the second criteria. And then, of course, support of and of course Hn lies between okay. So this is the one. This is the meaning of this. So this statement means the following. Hn is a continuous function with compact support defined on Vn. Okay. And of course, therefore, you can stretch it as a continuous function defined on the whole of x by putting it equal to identically equal to 0 on the complement of Vn. And this statement means that on Kn, Hn is identically 1. Support of Hn is contained in Vn and Hn lies between 0 and 1. Okay. And it's a continuous function. So something like this. See, I'll show you what exactly it is. So suppose this is your Tn. Then there is a compact set here, An. Then you have an open set N, such that the length of these two portions added together would be lying between is having length less than 2 to the power minus n epsilon. And then the function that you have, it will be something like this. See, it is 0 up to here, and then on this part, on Kn, it is going to be 1. The remaining portion, it is going to be something. But it's a continuous function. So this is the nature of the function. Okay. So it is 0 on this portion. This is your Kn. And on Vn, the function has its support inside Vn. And the value of the function lies between 0 and 1. And this is identically equal to 1 on Tn. Now this is the scenario that you. Now let us look at this function. So now we define G. So for each n, you have such a Hn. Let us complete this. Now define G. Two to the power minus n. Okay. So what do you get? Look at this series. Now this series is you see that each term of this is less than or equal to 2 to the power minus n. So you see that this is bounded by minus n, which is convergent. So this series majorizes this. Okay. So this is a convergent series. Therefore, what you can say, Gx uniformly convergent And each of this, because of this uniform convergence and continuous, G is continuous. With compact circuit. With compact circuit. And support of G and you see that 2 to the power minus n except on En minus k. Look at the definition. Except on this is equal to, otherwise except on this, see this is equal to 2 to the power minus n, Hn x is equal to nx. What does this mean? Which implies Gx equal to f of x, because you get this one, so you get each of this will become Tnx, and we have already shown that this sum of Tnx is equal to fx, but where? Not on this. This is equal to fx except on union of, this is the important. So G is a continuous function which is equal to fx except on this. So you can easily show that. We have there exists G belonging to CCX such that the measure of the set on which this is less than, because each of this has length less than 2 to the power minus n, and then now you times epsilon, and therefore you just add them up. Okay, so if you add them up, this is majorized by. So we have proved our result subject to the condition that f lies between 0 and 1. Now we just go further. Two things. We want to here we are talking about a real valued function. We want to go beyond that. So what you do is, now the relation 1 holds for A compact. because the condition that we need is mu A is finite. Okay, and F a bounded measurable function. Now the way in which you prove this is this. You bring this down to the theorem that we have proved. So suppose is less than n. Then you take this one, mod f. So you take consider 1 by m. Then you see that 1 by m f is measurable. But what you have is 1 by m is less than by our choice. Therefore, the theorem is applicable to this function. Okay, and you can approximate it by a g. So m times whatever approximation you get would serve the purpose, and you get it. Okay, so that is quite easy to do. Okay, so g, so there exists g tilde with the properties of so what do you do? So you define g to be equal to m times okay, then the theorem. So that is true. Now we remove the compactness restriction. We have assumed that A is compact. All that we assume now is that mu of A is bounded. That is fine. A not necessarily compact. This is what we are doing. What we observe is that if mu of A is finite, then A contains a compact set. Remember, you are working in a locally compact Hausdorff space. Okay, there exists a compact set A contained in A with measure of is as small the desired. That means you can approximate A from within by a compact set as closely as you want. That is, A can be approximated from within inside by a compact set which is as closely that is what it says. So we can make it, so if you choose an epsilon, you can make this mu of A minus K less than epsilon. You can choose K in make such a choice. So we take if F is a complex measurable function, if greater than n, then we have integral is an empty set. That is mu of Pn goes to 0. Now F coincides with the bounded function one minus chi Bn times F. So on Bn, this is going to be 0. Okay, and outside Bn, this is going to be F. That's the meaning of that. And outside that's the meaning of that. Therefore, we can work on this one, on the bounded function. Okay, and therefore, what is the consequence of that? F and get the approximation. GL. Therefore, from which you can read that the relation 1 holds in the general case. Now this is because mu of 0. Mu of dn goes to 0. So that is the proof of the theorem in that case. So we have proved the first statement in the general scenario. Now we have to prove the truth. What does the second statement say? The second statement says we may arrange G such that supremum of x belonging to x so that is now in a way approximating from below. Okay, because you can always keep the supremum of G less than or equal to supremum of F. This is given. Okay, so we have shown the existence of a G, but now this G can be chosen such that this additional condition is satisfied. This is the second condition that we have stated. Let us see how we work it out. It's very simple art. Now, having done the part 1, so there is a G in our hand. Now, from G we construct another function G1 possibly with this property. So, this is the one. So, having constructed so we have already constructed G with the property that G is a continuous function with compact support and the set on which G differs from F can be made arbitrarily small. So that has been achieved. Now we assert further that the G can be so chosen such that this inequality is satisfied. That means supremum of G is always less than or equal to the supremum of. How do we do that? It's quite easy. So we have to, so having constructed the G. Is less than epsilon. Given epsilon, we shall show that G can be replaced by a G1 with the properties of G and such that supremum so this G1 can be so chosen such that G1 satisfies all the properties of G and as well as this. Okay, so so let R be equal to supremum of so let R denote this. Okay, that is, it's a bounded function. Now define set whenever mod Z with this R and equal to R divided by R into Z divided by mod Z. Greater than. So this is the definition. Okay. So this is the definition of what does this do? Let us just try to understand this function. It's a very standard technique. So this here you are describing a map from the complex plane to the complex plane. Now what we have is we have got a circle of radius or a disk of radius r. What we are doing is we are mapping phi from here to this. Okay. So this is a bounded set. This is not a bounded set. Okay. So what we have is this is phi which carries this unbounded set and through a continuous map to the bounded set R. How does it happen? You take this portion, the disk of radius R. On the disk of radius R, the function restricted to the disk of radius R is the identity function. Okay. That means every point x here goes to nx. Now what happens to points outside? Points outside, so you take a point outside. What you do is you project this to the boundary here along the radial line. How do you do that? So suppose this is your z. Okay. Now z by mod z, z by mod z is a projection to the unit circle. Okay, is a projection to the unit circle, because you see that we are not changing. See, z you take as r e to the power I theta, r greater than r. Okay, then what happens? Z by mod z equal to e to the power I theta. So it is the same, the vector with the same argument theta, but now the length of the vector is taken as. Now what you do? You scale it up with r, multiply by r. Then what happens? R z by mod z equal to r e to the power I theta. So what you are doing is, small r e to the power I theta is now projected to capital R e to the power I theta without changing the argument of the vector. So that is the behavior of phi. So you see that every point in this complex plane is mapped to the disk, the bounded set disk. Is this a continuous map? Yes, it's a continuous map. Right? So we take that continuous map. So understand this map. How do we use it? How do we use it? As I said before, we have already got the G. Now G is a map. This is your X, and G is a map to C. Right? And now from here, you take the map to the complex plane again, C, which is your phi. Therefore, what is the range? The range is this one. Supremum mod x. Okay. So you have the composition map of this going from here to here, which is G1 equal to G phi composition. Now this G1 G1 is a continuous. Okay, right? So what can you say about G1? So you define G1 to be equal to phi composition G, and G1 satisfies 1. Why it satisfies 1? Because you see that F is bounded by this. So outside this, even if you take it's a measurable function, is the outside, you know, the what you call Yeah, okay, let us look at this one. So let us take these two functions g1f and g1x. Now you see that g1x equal to gx equal to gx for every x belonging to x such that gx so f is defined in some places. So you take the domain of this is fx, or this is where less than or equal to r. Because f is a bounded function. Okay. Outside it's going to be. Therefore, here for fx less than r and x belonging to x such that mod fx less than r, g1x is equal to gx. Therefore, you see, let us work out the set where what do you get? We are working out the set x such that this is actually two parts. This is equal to gx, but mod fx that is one part. Okay, the other one is union split this into this, because on this one g1 is equal to g. That is why I written here. It's not a mistake. Okay, because here on this g. So what happens to the measure of this? This, of course, you see that is a part of the okay. This is 0 because you are assuming f is bounded by r. Therefore, this is equal to. Therefore, you see that supremum of or mu of Ex. Okay, and this is less than epsilon. That's how we have chosen. So that condition is satisfied, but now what we have to examine is, so condition 1 is true. And G1 is a continuous function, compact sum. So everything is nice. What more? What more we will need is this. So you have to show the condition 2. Now you see that supremum of mod G1x. Okay. Mod G1x is less than or equal to R. That's equal to therefore 2 for G1, whereas 2 may not hold for G. So we first make the choice of G and then construct from that a G1 which satisfies the condition 1 as well as the condition. So it's always possible to construct a G with satisfying the second condition. Okay, I think today we will stop here, and there's a corollary of this theorem which I shall do next time. Okay, thank you very much.